fan or a family member of somebody who had designed the Titanic, I would be very offended by that joke. Seeing as I am neither, how's everyone doing? It's Monday. Everyone must be excited to be back at school like I am. Yeah, I didn't want to get up this morning either. But here we are. Of course, we all look forward to chemistry class. It's like magic, but it's real. So I thought we could definitely use, as discussed, a bit more practice with stoichiometry and enthalpy. So today we will do lesson 3.5, a little more stoichiometry with enthalpy. So I'll bring this around for you, and we're just going to go through some typical kind of enthalpy problems you might come across in your chemistry wanderings.
Wait a second.
Well, it's like anything else. If you wandered through the museum by wandering actually through all of the objects in it, you should avoid like the history of medieval weaponry display. But you know, as long as you wander around the dangerous things, you're cool. You can enjoy it. Likewise with chemistry, it's a curated visit through chemistry. We're going to keep you safe, kids.
But then that's no fun.
Listen. Okay. In grade 11, you will have done so much stoichiometry that it made your teeth hurt. Right? Lots and 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 lots of stoichiometry, right? And if you remember, that's right, if you remember, the central thing to all of stoichiometry is what? Stoichiometry always comes back to, definitely, a balanced chemical equation, which tells you the ratio of how many. A balanced chemical equation does not tell you the ratio of how many grams of things are used. Moles. So I always like to draw this little kind of map, mental diagram for myself, which is this. If I know how many moles of something I have, what letter do I use to symbolize that? N. N for number of moles. If I know that, what are some things I can figure out? Yeah, I could definitely figure out mass. What letter do we use to symbolize mass? And we measure that most typically in grams. And I can go back and forth between these. What's the only information I need to do that? Yeah, I need to know the molar mass. Where do I find that? Yeah, just on the periodic table. So all I need to do to go from mass to moles, or from moles to mass, is know its atomic weight, which is just found on the periodic table. Obviously, if it's a compound, you'll have to add them together, but that's just arithmetic. Does that make sense? What else can I figure out if I know how many moles of something I have? Yep, mass, we've done that one. What else could we figure out? Totally true. Yeah, so we could figure out volume in liters, or pressure in kilopascals, or temperature in Kelvin. What relationship is that? Concentration is another one, definitely. And we measure concentration usually in what? Moles per liter. And to learn that, what information do we need? It's easy. We know the moles. We just need, so we just need to know the volume, definitely. But down here, when we're talking volume, pressure, and temperature, what are we talking about here? Are we talking about concentration in liquids? No, we're talking about gases. What's the equation that we use for all of our gas-related needs? Oh, come on, the ideal gas law. It was not that long ago for you, team. Come on, people who took a couple years ago, show my students up who are obviously poorly taught. Show them that Smith's lessons hang on 2 years in better than mine 3 weeks later. Yeah, what do you got? Very good. So we can go back to the ideal gas law. If you remember that, PV equals nRT. This is for gases. And remember, R is a constant. You can look it up. Anyone remember it? 8.314 liters kilopascals per Kelvin mole. Don't worry about it. You can look it up. Easy to find. Don't worry, we're going to do one of those today, so you'll get some practice. Now, obviously, I could also figure out this thing that I'm never going to ask you. But, yeah, the actual number of atoms or molecules. And what do you need to know to do that? Yeah, which just tells me that 1 mole is very good. So a mole of something is 6.02 times 10 to the 23rd. I could actually ask you to tell me how many actual hydrogen atoms there are in the reaction. I am never going to ask you that because I don't care. Because I can't measure out individual atoms. But that's another thing we could know. But now we have one more thing we can learn. And that's what this unit is about, of course. I can also learn delta H, which is measured in what? Nope. Joules, or kilojoules, of course. And to do that, I need to know the molar delta H, which will be some number in kilojoules per mole. And this is either empirical data, you could figure it out yourself if the experiment called for that. More often than that, you just look it up in a table, right? There are big tables. Now they're all online, which is nice. When I was a chemistry student, you had to go look at them in a book. Books, you'll know, were these things that had paper inside of them with things written on it and covers, and you could open them and read. They were like tablets that were made out of like hundreds of little mini tablets with displays that were stuck on one thing. And you could kind of flip between them. Yeah. That's what, yeah. Literally, we killed trees so we could write down about how we should save the trees. It was a weird time in human history. Anyway, and we could actually even go one step further with this, and I find this map to be very helpful. Once we know delta H, we can actually usually figure out the change in temperature because we know what equation is also true. Q equals mc delta T, very good. And for all intents and purposes, Q is, of course, heat. Delta H is change in enthalpy. But we can remember that for all intents and purposes, Q will be the absolute value of delta H, right? In other words, we are going to assume in this course that all of the enthalpy that is lost or gained in a reaction does so in the form of heat. We know that in reality, that's not true. Reactions aren't 100% efficient in converting chemical energy to heat energy, right? We know they also make light and they make sound and they cause motion and other things that use energy. But for the purpose of this course, and you'll see that it mostly works in reality, we can approximate that Q is equal to the change in delta H. So if we know what delta H was, we can go ahead and say that's Q. And of course, we ignore the negative sign because a negative delta H, does that mean that there was anti-energy created? Anti-energy. Wow. Is that what we did? Yeah, it just means that it was going in one direction or the other. By the way, a negative delta H, is that energy released or energy absorbed? Oh, good, we disagree. All right. You two are going to have a battle of, you should have a thumb war. Do people still have thumb wars?
Yeah.
This was a big thing when I was in grade, say like 5.
My little sister's.
All right, what did you say? All right, so he won the thumb war.
Yeah. That's why I said it very.
A negative delta H, remember, delta H measures the enthalpy inside the molecules. So if the energy inside the molecules is going down, where must that energy be going? If there's less energy in the molecules, then that energy must be outside of the molecules, right? So a negative delta H means energy is released. What do we name that type of reaction? Exothermic. Good. On the other hand, if delta H is positive, that means the energy inside those molecules is going up. Where is that energy coming from? The outside. It's going into the atoms. It's coming from the surroundings. What would I observe in the surrounding environment in that case? It's going to get colder. It's going to decrease in temperature. Good. And we call that endothermic. Endothermic. Okay. Again, we're going to do lots of practice with this. I will never test you on a map like this or anything like that. This is a visual aid that I find really helpful to remind myself when I go to do a question how I should approach it. What is the central hub of this? Moles. So to go from mass to a change in temperature, what path would I have to follow? See what's nice about this? Say a question gives me the mass of something and says, what will the change in temperature be? I can draw that right on here. I'm going to start with mass. I'm going to figure out how many moles I have. From that, I'm going to figure out my enthalpy. And from that, I will figure out my change in temperature. Does that make sense? And it draws the map right for me. Now I know what my dimensional analysis is going to look like. I can see what my calculations will be. I will start with grams. I will go from grams to moles. I will go from moles to joules or kilojoules, depending. Moules, which, if I'm not mistaken, is French for muscles, like the food you eat. So there you go. And then from that, I will, the more you know. And I worked at a French bistro once. And then from that, I will figure out my change in temperature. And of course, temperature will be most commonly measured in Celsius. If you are not kilojoules, temperature will be measured. Celsius would be okay. Better than Celsius? Kelvin. But we'll say either. Both are cool. Both work. Okay. So again, this, not a bad thing to acquaint yourself with. From there, we're going to do some stoichiometry today, which again, stoichiometry just means using these relationships to determine anything quantitative about a chemical reaction. So in this case, here we go. And if you remember from our lesson on representing enthalpy change, one of the ways we can represent an enthalpy change is we can just show that energy right in the reaction. So here we have a reaction where we take C4H10, what is that? Butane. So butane reacts with oxygen, and what's it make? Water, carbon dioxide, and what else does it make? Yeah, it releases energy. It releases 2,877.6 kilojoules. For every 1 mole of butane that gets used, we get 4 moles of carbon dioxide, 5 moles of water, and we make, not make, but we release 2,877.6 kilojoules of energy. What kind of reaction is this? What kind of reaction is this? Sorry? It's a combustion reaction. Very good. And combustion reactions are exothermic. Good. Very good. Okay. Here's my question. When a sample of butane is burned, 3,425.2 kilojoules of energy are released. How many moles of butane were reacted? And then I'm going to add a B part to that. How many grams? So take a minute, give this a crack. Try it. We're going to use dimensional analysis. We're going to use the information we have. You can refer back to our little map here to give you a sense of how we're going to answer this. I'm going to eat my banana. If you don't know what to do, put your hand up and ask. Don't be shy. What did you say? Okay. Well, you don't get the first part. Take a look. Yeah. If Rebecca is, she would love to. Oh yeah, that's all. Do you want to grab them? The whole class. Yeah. Yes, let's take a look. What am I thinking about this round? In this game? Okay, that much. And what's that measure? So what have I actually told you? I focus mass, I have to look at the changes. I told you the change in. Good, the change in enthalpy. See, I know that. And my question is asking us to go to how many steps is that? Just one. And then when you go to grams, how many steps is that? Yeah, so it's actually a pretty easy question. So it's not so bad. Now what's going to be a stretch for you is if, again, you guys, I don't know how you were taught to do the stoichiometry. If you make shown dimensional analysis, there's lots of different ways you do that shown. And they're all good, nothing wrong with any of them. But I'm going to so for dimensional analysis, start at the beginning, let's write it down. So we learn that, ready to do some calculations. I mean, it's hard to when we do dimensional analysis, you take it from given, well, multiply by right there. Right. So show. Oh, no. Take a look at the chart. And now, this information, where are you going to get another chart? You need to know how many moles of your stuff related to how many.
No, it's just. I was thinking about like it's like the same amount of
No, that would be a kilomole, which isn't what we're talking about. Where do you figure out how many kilojoules of energy you get when you burn that stuff? Yeah, because if you look, what's the reaction? How many moles of urine in this reaction? How many moles of all of your dreams?
Only my face.
Yeah, which is what, 13 over 2, that's what, 6.5? So 1 mole of butane will react with 6.5 moles of water. What will it make? Sure, what's this? How much? Good, what's this? How much? Good, what is this? Good, how much? You got it. So we know that for every mole of this that we use, we made that much energy. Cool. So now do that calculation. Right. There you go, if you'd like. You got them? Calculus? Nice of the phone, yeah? Yeah. Calculators? Leave it out. Yes. This is what happened when you took a bunch of this and you burned it. Now, if I had burned exactly 1 mole of this, how much do you get? Yeah, that's right. That's what this reaction says. 1 mole of this plus this is how much actually happens. So let me ask you this. What? Okay. If I had 1 child, how many eyes would I get? But there's 6 eyes in my house that belong to my children. That's it means. Good. So talking about this. No cycle. No, I know. It's like a TV. We're talking about this. Yes. It's bigger than TV. Bigger than Yep. Yeah. Allow me. Is there anything else you'd like, Jay?
Well, like I thought.
Can I bring you a coffee? Maybe
Actually, yeah.
would you like a warm blanket?
Yeah, wait, I got a sneaky way.
You got it? You got it.
It's a sneaky way, but it'll give me the answer.
Add granola bars now, they're gone. I actually want one.
Is my lunch supply gone?
Oh, yeah.
Oh, is it? I'll replace it this week. You gotta let me know when it runs out.
I finished it off about.
Yeah.
Yeah, no, remind me. I like to have it stocked.
No, yeah, it's great. I don't need one. I just don't have-
Cool, do the beat part. Tell me how many grams.
No, I didn't.
Is there anyone who feels lost? Anyone I can help out?
Yeah, I still.
You're at a loss.
Like, well, yeah, I'm not very sheet or like. I thought I could divide this,
Yeah,
but
like you've lost someone.
this.
I've done one.
So 1 mole of this.
Like in a grocery store, like there was Walmart. I was playing the clothing racks, and then my dad was like,
Yeah.
They brought it.
Okay, I thought it was like.
You got this.
Right.
You got this. Again, anyone feeling lost? Or feeling all right? Because if we're lost team, we're lost together. Jim Cuddy taught me that. Maybe Blue Rodeo reference is a bit too aged for this crowd. I don't know. You tell your parents that, they'll think it's funny. I mean, not ha-ha funny, but cruel.
So my guesstimate was right.
I once had a student tell me I was funny, and then he followed up by saying, and this is true, not like ha-ha funny, but, you know, like funny looking. I was hurt. Anyway, it's the end of my story.
At least you know.
No, it's not like saying, well, at least he robbed a bank. Like, you can't just put at least in front of something and it makes it good. Just stop. Just stop. The mark just dropped 5%. I want you to know that. Use it again and see what happens, Alondra. Okay. And I meant it, internet. Okay, let's take a look at this one. Starts with some nice, simple stoichiometry. Let's look at our map here. What information have I given you? I gave you a chemical reaction, but in terms of the actual question, I only told you one thing. What did I tell you? Yeah, I told you that there's, 3,000 something joules of energy? From this map, what information have I actually given you? Yeah, I've given you delta H, right? It's the only thing that's measured in joules or kilojoules. And what have I asked you to tell me? I've said, if this much energy is released, tell me what? Eventually, how many grams? But first, how many moles? Where is that? Right below it. How many calculations am I going to have to do to answer this question? This first part. Just one. After that, I ask you to tell me how many grams. What am I going to do there? I'm going to use the molar mass. And how many calculations am I going to have to do to answer that? Just one. So this is only if I did this all in one, it would just be a two-step equation. But I've actually asked you to break it down into pieces. So let's break it down. We start with what information again? Sorry? Good, good. Being wrong is the first step in being right. yeah, I've given you the balanced chemical equation. How am I going to start my calculations? You're right. We definitely need a balanced chemical equation. And not just a chemical equation. Since we're using delta H's, we need a balanced thermochemical equation. That equation has to include an energy component to it, right? Luckily, we have that. We know that for every 1 mole of butane, we make this much heat energy, right? Okay, so help me out. What's going on here? How do I calculate this? What do you think? Yeah, sure. We're doing the first part. You're going to tell me how many moles of butane reacted. Well, you're going to tell me how to find it. Cool. That should be a capital J, by the way. Sorry. So I want to convert from kilojoules, which you put at the bottom, and on top I want to put moles. All right, somebody else, help me out. What information will make this true? I need to know how many moles relate to how many kilojoules. Avery, you got that? No, that's okay. You're following along though? Okay. Yeah.
And don't try to make this wrong. You're going to try 1 mole, which is the one on the top.
I am trying. I want you to know. So you better be very specific.
2,877.6 at the bottom. No.
The bottom. Okay, and what goes on the bottom now? All right. I knew what you meant. I was just being difficult. Yeah, 2,877.6 kilojoules at the bottom. The reason we can do that, because we know from the balanced chemical equation, 1 mole of butane reacts with 13/2 moles of oxygen, which is annoying, but that's 6.5 moles of oxygen needed to make 4 moles of carbon dioxide, 5 moles of water, and it makes 2,877.6 kilojoules of energy. So I'm going to change colors. So that's really dark, isn't it? All right. You know,
Wait a minute.
take it away, Jade. Jade, thoughts? Thoughts? Well, this might be a good time to mention that on my screen, that looked really good. See? That's what I'm saying. All right, so there we go. That was like music to my soul. All right. And then when we actually do this calculation, by the way, just by eyeball, what do I know this is going to be roughly? What's it going to be between? What's it definitely bigger than and definitely smaller than? Before I do any math. Yeah, it's definitely between 1 and 2, right? Because I'm dividing 3,000 by roughly 3,000, right? This rounds to 3,000, that rounds to 3,000. But this is a little bit bigger, and that's a little bit smaller. But it's not twice as big. So it's going to be between 1 and 2. My instinct says 1.3-ish. What do we got?
1.1903.
I'm glad Caleb isn't here right now, because you know exactly what he'd say. Oh, you're off by just 1. And you're like, you know what, Caleb? Shut up. Yeah, I hope you're listening right now. No, I don't mean shut up. That was rude. I find your banter charming and whatever. Okay. What do we get? 1 point. 1 point. 19027497.
No, what's going on?
Okay, by the way, this is moles of C4H10, right? And what do I want to do with that answer? Okay, yeah, this is how many sig figs? 5. This is how many sig figs? 5. How many sig figs is this? 1 sig fig. Is that correct? Yeah, that's a counting number, right? We are saying exactly 1 mole, which means that is infinitely significant. We don't need to consider it. So I need this to go to 5. 1, 2, 3, 4, 5, which means I need all these to go away. Does this round up or down? It's going to round up. So my answer will be 1.1903 moles of C4H10. All right. And I am going to the box around that, because that is the answer to this question, which is good. What did I ask you next?
How many grams?
How many grams? Have we done this yet? All right, take a minute and do it. Okay. Take a minute and do it. Should not take you long. We're not only going to get good at these, we're going to get quick at these. All right? Let's get moving. Tell me, if I know how many moles I've got, tell me how many grams I've got. So you got that? Never do that.
Yes, talking to.
There are so many layers of this that are not acceptable. So let's just not break them down. I'll have to do that again. What is that? Like, first of all, it's not 2014. Secondly,
I said you. No. Okay. What if it works?
allow that. Okay, I'm going to put that
You
here.
get together?
Really happy with that. I know everyone does.
Well, like not everyone, right? Like if you're in a court of law, you know, because you're in a lawsuit, you wouldn't call the judge bro, right? Like that's.
Nope.
Actually, I'd like to
Honestly,
throw-
with police, I'm not too sure.
I mean, you could, but you would lose.
If I'm
Just,
really- if
like,
I'm really
that would be the moment the judge made his mind up. And the rest of this just wouldn't matter.
The judge is a bro.
You know, he's not. I don't know the judge, and he might be a she, by the way, because there's female judges as well. But all the same, all the same.
If the judge was your brother, I'm pretty sure.
That's right. That's right. And if I were the judge, I would take that moment to say, have we just declared a conflict of interest? I'm handing this case off. Charging you for the cost of having had to do this twice. Bro. She's the boss, applesauce. You don't talk that way to Judge Judy.
Thanks a lot.
Okay. Shh. Now again, let's take a look at our little kind of mental map here. Once we know how many moles we have, this is an elementary thing. We're doing dimensional analysis. Again, how many steps is it going to be? Just one. What piece of information am I going to need to know about butane? I'm going to need to know its molar mass. Where do I find its molar mass? In the periodic table. Good. We've become mute, but that's okay. That's okay. I saw those hand motions. So, somebody tell me, what's this calculation going to look like? Okay, go. So what's my number? Very good. And from there, what do I do? Very good. Are both of those also C4H10? Cool. No. Yeah. He is. He'd be delighted to. All right. And what do I put in here? In how many moles? In 1 mole. Okay. 2 questions for you. First question. Why did I not put 1.1903 down here? Because that's how many moles I have. Sure. But when you looked at the periodic table, that tells you how many grams are in 1 mole. Good. Second question. How'd you get this number? Great. And I'm going to just show that really quickly here. 12.011. Sorry? Yeah. By the way, on a test, you'd all have the same periodic table. If you use the periodic table you've got, which may mean you have slightly different answers from one another, that's okay. And then plus 10 times 1.0079, is it 794? 5?
Well, it's like 5
Is it
here
4?
and 4 up there.
Whatever. Okay. So your mileage may vary ever so slightly here. That's fine. What did you get when you did this calculation? Yeah. Yeah, I'm using your numbers, so we should. Okay, now the whole thing.
Oh,
Yep.
okay.
Yep.
69.1.
Very good. And you've already gone ahead and put that to the correct number of significant digits, right? Perfect. And what's the unit? Very good. Is that starting to feel comfortable? Specifically to those who didn't take grade 11 last semester with me. Is that starting to feel a little comfortable? Is that very different from how you did things like this in grade 11? Is it? Okay. Well, we'll just call it a blank slate then. This is how we're going to do it in this class. Again, you can approach a question like this. It would require, this simple question would have required 4 different formulas, 4 different setups, 4 times where you put all your variables on the left and wrote down what they were. There's nothing wrong with that. It's just cumbersome. This way we just work it out logically. Having said that, it does take some practice. So questions about that, comments, concerns, thoughts, hopes, prayers, dreams, nightmares, ambitions, pamphlets, future goals, past goals that you want to mention having successfully achieved or failed to achieve. We're good? All right. So let's try another one. Here, I'm going to ask you to go to the mass directly. All right. So in the last one, we broke it down and did it in 2 steps. This time, we're going to do it in 1 calculation. All right. Basically the same question. Another thing, instead of putting the energy into the equation, I've gone and written it on the side as a delta H. You need to know which side of the equation it goes on, children. Yeah. I mean, in this case, you'll figure it out. But, and you know what? I think I thought I was being clever by making this the same number, but that was lazy. Let's, I really do think that at the time I was like, this will be clever, but let's not do that. Let's say negative, oh, I don't know, 8.6. Yeah, I like that better. Sorry? Yeah, no, that's a good number. I like that number. Okay, let's do that. So change that to 8.6 and let's go. This is why I shouldn't plan lessons at like 11 p.m. because I'm like, oh, it'll be really clever. I'll make the delta H for the question the same as the reaction, but then that's just boring because you can just skip a whole step of math. So there you go. Okay. A little confused. I've said delta H twice, right? What's that mean? But remember, one of the ways we can show the energy involved in the reaction is like the last question, put it in the equation. But another way we can do it is to show the equation and then put the delta H to the right. Now in that case, even though it doesn't say it in the unit, we know that this is kilojoules per mole because that's the delta H of this reaction. And how many moles were used in this reaction? 1. Does that make sense? By the way, how many moles of oxygen were used in this reaction? 2. How many moles of carbon dioxide were made in this reaction? 1. How many moles of water were made in this reaction? Goes. How many kilojoules of energy were released when we used 1 mole of CH4 and 2 moles of oxygen to make 1 mole of CO2 and 2 moles of water? Good. Now, in our actual reaction, did we use 1 mole, 2 mole, 1 mole, and make 1 mole and 2 mole? No. We used a different amount because instead of releasing 2.5 kilojoules of energy, we released 8.6. Hey, did we use more than 2 moles of water or of oxygen or less than 2 moles of oxygen? We use more oxygen or less oxygen in our actual reaction. More, right? Do you think I used double? Like more than double? More than triple? Yes. So they give you nice numbers to work with here, right? Did I use up to quadruple?
No.
No. So I can do a sense of where they're going with this. So I used somewhere between 3 and 4 moles of CH4, right? Because 2.5 is a nice number, like, right? Double that would be -5, but I released more than -5. Triple that would be -7.5, and I released more than that. Quadruple that would be -10, right? Which I didn't reach. So you have kind of a sense of what your answer should look like. Anyway, get to it. Give it a try. I want one calculation. You got lost. Go ahead. Yes, ma'am.
This was not produced by the oxygen or oxygen.
It's released by this reaction. In other words, if you took the oxygen away, this reaction would happen. If you took the CH4 away, this reaction would happen. So this is the result of this whole reaction.
So I have to write that entire thing beside the column.
Nope. Well, that's not true. Well, that's true, but that's not. Look at your reaction.
I don't know.
What did you say up here? Yeah, is that true? How many moles left? Right? Yeah. Good. We're doing. Feel a little lost? Where are you definitely going to start? That's the only information that you need. Yeah, this is part of the equation. That's okay, we'll get to that. But the only thing that I've given to you is question. So that's definitely ridiculous. So start with that. And let's go back to this idea of mapping it out. Jade Bar, let me come to you. What information have I started you with? That information you just wrote down, what is it? Great, so on this map, I'm going to give you a highlighter. Highlight whatever. Good, and where do I want you to go? Question says, yeah, so how are you going to get there? Beautiful. How many steps and how many fractions will you have to draw in your dimensional analysis?
2.
Good. What will the units be in the first one?
Moles.
Great. And then the second one?
Grams.
Cool. Do it. Even before you put numbers in, now you know what the units are. So set your fractions up and then find the numbers in the question. Again, don't be shy. If you're feeling lost, put your hand up. Oh, that's nice. I think I like that. In fact, I'm sure I like that. I mean, there's a lot of different ways to do the same thing, but reading the question is probably a good start, universally speaking. Yes. I promise I will not give you any questions in Swahili or Esperanto.
Well, that reads out every other language.
Correct. Ça c'est vrai, madame. Oui, oui, oui. Pour cette question, qu'est-ce que c'est le premier processus, s'il vous plaît? Qu'est-ce qu'on dit pour cette question? Allons écrire qu'est-ce que c'est? Quel dommage. Et ainsi? Oui. Cool. Do I wish I'd left myself a bit more space? I think I do. Okay, who wants to give me numbers for this? By the way, moles of what? What's my question about? I mean, I could do that. You're totally right. I could do CH4, but what's the question I'm asking about? Yeah, so you would not be wrong to do CH4. You would not be wrong, but you might not be answering my question, because my question is what mass of oxygen? So what should I do moles of? Oxygen. Again, keep in mind, like, you can do things that are mathematically correct and true and not be answering the questions. Right? Like if I said spell cat and you said dog is spelled D-O-G, you're right. I'm going to answer my question. What numbers could I put in here now? Okay. And? Well, how many kilojoules of energy are used in this reaction? Very good. And we're close. We are really close. So this information comes because we know that when I carry out this reaction, I should get this much energy per, you're totally right, 1 mole of CH4. But keep in mind, since we're not talking about CH4, what are we talking about? Oxygen. So what's my number? How many moles of oxygen? Good. Does that make sense? You had a 1 which was correct when you had CH4 there. But now that we're talking about oxygen, we just got to make sure we check it and say, okay, in the equation, there's 2 moles of oxygen. And I'm going to take a moment and like highlight this so we can see where those numbers came from. We have 2 moles of oxygen because that's there. And we have, oh, I don't know, that's a lovely color. They're great because they're like nice spring-like colors, just like our weather. Okay, if I stopped calculating now, what cancels? Good. So if I were to stop calculating now, what would I know? What would I know if I stopped calculating now? I would know how many moles of oxygen I must have used in this reaction, which is really close. But what does the question ask? Yeah, it asks what mass of oxygen. So I need one more step. And what's that step going to call for me to do? Just units first, no numbers. What do we got? What do you think? Yeah. What's my next step going to be here? Very good. Great. And in both these cases, I'm talking about oxygen. Good. Oh. So moles of oxygen and grams of oxygen. Now, where do I always get the numbers to know how many grams are in a mole of something? Where do I always find those numbers? Always, always, always. There's only one place I look. It's like if you're looking for eggs, you're only going to the fridge. You're not going to check the cupboards unless you've done something horribly, horribly wrong. I suppose. And I suppose you could also go to the internet or a textbook for this, but you know what I'm driving at. Where do I look in just... you guys make me so sad. Where do I always look to find a molar mass? The periodic table. So 1 mole of O2 weighs how much? 1 mole of O weighs 16, 15.99994. So a mole of O2, because of course oxygen is diatomic. She's a Hofbrinkel. You guys haven't made a mistake yet, so I'm not making you, though, if you're really keen. So what number goes up here? We have to take that 15.9994 and do what with it? Double it, right? We would say the mass of O2, again, you don't have to write this out, but if you felt so inclined, you would say it's 2 times 15.9994 grams per mole, and that's going to give us what? 31.99986? Is that true? Oh, okay. Oh, because that's a 4. Right.
And then times 9.
Whatever, I'm going to trust that you're right. Is that correct? Okay, good. And what will cancel now, unit-wise? Molos. All right. Good job, bro. So if we look here, let's just remind ourselves what we've just done. We started by saying, given this reaction, when I actually did it, I didn't use perfect molar amounts because I didn't. But when I did the reaction, I measured that the enthalpy change was 8.6 times 10 to the 2 kilojoules. It was negative. That heat was released. Given that, I want to know how much oxygen I must have used up. I can do that because I know that for every 2 moles of oxygen I use, I release 2.5 times 10 to the 2 kilojoules of energy. And that's what I do here. So I can use the balanced thermochemical equation to figure out how many moles of oxygen I used. Because 2 moles of oxygen gives us that much energy. Does that make sense? You go to the equation. And once I know that, the only step is the question didn't ask me how many moles of oxygen. It asked me the mass of oxygen. And that's a very common step. That's the most common calculation you're going to do, right? Mass to moles, moles to mass happens all the time. And to figure that out, I just look at the periodic table and I say 31.9988 grams of oxygen is the mass of 1 mole of oxygen. And once I've done that, what number am I going to get? I'm going to get something on the order of what? 150? 100? No, 170, 180? What do we got? Anyone? Has somebody done this calculation? Take a minute and do the calculation. Don't just wait for Jade to tell you. Have you done it yet?
Like about 170 to 180. Oh, no.
A couple 220.
That makes sense. Yeah, that makes perfect sense. So 220? Okay, and what did you get before you rounded? 220? 1517. And how many sig figs do I actually want in this? I want 2, right? This is 2 sig figs. This is 2 sig figs. What about this 2 up here? How many sig figs do I have there? I have all of the sig figs. What about this 1 down here? All the figs, and all of them are sig. And this one here? No. I have 6 of them. So obviously my answer needs to have
2.
2 is correct. So those guys are going to get canceled, and that 2 is going to round up or down. Yeah, it's going to round down, right? It's going to stay where it is. And so the answer will be what? 220 grams of O2. If you like to be really unambiguous, you could put that in scientific notation. If I wanted to put in scientific notation, what would that be?
2.2 times 10.
Yeah. Frankly, I think that's unnecessary. I would just write it as 220. But if you're a keener type, you could write that as 2.2 times 10 to the 2. That's good to be a keener type. Nothing wrong with that. Questions about that? Does that feel okay? Tell me if it doesn't. Again, the stoichiometry thing, it won't go away, I promise. So we're going to do lots of practice, but if you feel lost by it and you think maybe some one-on-one help would be a benefit, come get some one-on-one help. I'm friendly. I might even like share my cookies with you at lunch. Do I have cookies today? I don't have cookies today. But that don't let that mean you shouldn't come for help. But like tomorrow, if I have cookies, I would share one if you came for chemistry help, whatever. Sorry? Am I bribing you to come get help? No. I'm not sure you understand what bribery is or how it works.
Well, it depends on what you're getting.
I just picture Kendra going to the gas station and like filling up, and then the guy says, "That'll be $10," and being like, "That a bribe?" Like that didn't make any sense, Miss Schaefer. Be like, "I'm reporting you to your authorities." All right. I promised I'd give you one tricky one. So here's one tricky one. What volume of CO2 will be produced, assuming atmospheric pressure at the end of a reaction is 101.3 kilopascals and the ambient temperature is 20 degrees Celsius? So we're going to do this same reaction from above, same reaction, only this time we're going to work our way to a volume of CO2. Okay? Can I give you some advice? To figure out the volume of a gas, what equation are we going to use? Puvnert is correct. Okay. So, yes, we are going to use, what's Puvnert actually mean?
Pressure, volume equals MRT.
Okay. So let's talk about these one at a time before we do the math. What does P equal in this question? You already know. I gave it to you in the question. Yeah, so P stands for pressure. We've got 101.3 kilopascals. So that is our first. V is what I'm asking you to find, is it not? Okay, so we're going to have to make that a question mark because we don't know. Okay. N. Uh-oh. We don't know it, but we're going to have to find it. That's going to be the first half of this question. That make sense? Oh, I did not leave myself enough room, but that's okay. We'll just go up here. What is R? It's a constant. We have to look it up. Does anyone remember it? There are two. We're working with kilopascals here. Does anyone remember the kilopascals one? That's the other one. But this one is 8.314 liters, kilopascals per, what goes on the bottom? Kelvin mole. Good. Again, you do not need to have that memorized. But good on you if you do. But it'll always be on a test. It's always in textbook. You can always look it up. And temperature in this case is what? 20 degrees Celsius. Can I use that in this equation? No, I need to use Kelvin. Does anyone remember how we convert from Celsius to Kelvin? Very good. Which gives us what? We're just going to leave it here. We'll round at the end of the question. Because this isn't in the end what I'm looking for. Just remember that when we go to finally do sig figs, it'll be based on this. And spoiler alert, it's only one. But actually, you know what? We should use the addition rounding rules here, and we should call this 290 Kelvin. That would be a more appropriate thing to do. Okay? Remember, when you add sig figs, you don't count significant figures. You make sure that it is the lowest number of decimal places. In this case, to the nearest 10. And this is measured now to the nearest 10. Okay, so the only thing you're missing is N. So this is going to be easy. When we solve for volume, by the way, what are we going to have to do to make this a solve for volume? Divide both sides by P. And so we will get volume is equal to nRT divided by P. So we're ready. The only thing we need is N, right? So really, this question over here is just to figure out N of, yeah, but N of carbon dioxide. So go ahead and do that. Did you guys miss ideal gas laws?
Yeah.
Yeah. I like that stuff. I think it's neat. I think it's neat that you can predict how big a balloon you'd be able to make by doing a reaction.
Right here. You can feel it and hear it. You have a broken leg. Graphite. Which means all value pencils. So what are you
I'm working on that. Well, that one is also good. I'm of all of them, but I'm proud that this is my idea. And I'm allowed to have one good idea every 5 years. So I had a good idea. And they're doing it. They are going to that room because we do not, yeah, we do not need 4 science labs. in a school. I mean, University Secondary School has 1 science lab, and another school has like 8. So like we are over-equipped in terms of lab space. We're taking that one and we're going to do a vertical whiteboard. So all the walls we just do whiteboards. And then we're making tables, but the surfaces are white. And so it's just a space you can go in, whatever, you can teach it whatever, but if you just want lots of space to work on stuff and work on ideas. I had one at South Lincoln. Similar, it wasn't that good. My chemistry lab there, they at least put one wall of whiteboards in for me. It's a great way to take the work you do. And to spend ludicrous amounts of money on whiteboard. I don't know that I agree with that, but okay. We'll do this question. And again, if you lost, then ask some better. Yeah, I used to do that at a different. Yeah, I was like that. Yeah, no, it's less fun when the weather is the same as Christmas. Spring.
Yeah, that's what it is.
Also known as spring.
I think that's just a dog. Yeah.
Snowing in my soul.
That's kind of
Sorry?
I think that's kind of inconvenient. Oh no, it's been.
You're telling me.
It's supposed to snow tomorrow, not Wednesday. It's the middle of April.
Okay. So if we go back and make a map of this guy, we see that this is actually a pretty simple question. I've given you, back from the original question, I gave you a delta H. And again, I'm asking you to find number of moles. Now, mind you, this time, number of moles of what? CO2. Yeah, not oxygen this time, but carbon dioxide. And then from there, I'm asking you to find the volume produced, right? We are setting this up as a separate equation. You could do it in your dimensional analysis. It's clunky. This is a case where the equation is just nicer, I think. Though you could certainly do it using dimensional analysis. So lay this out for me. What do I know in this question? Again, what's the only information I start with? No, this is going to all help us with this. But to get the actual stoichiometry, I haven't given you any information about the reaction here. But it's the same question as this one. Yeah? So what do I know? I know that we released 8.6 times 10 to the 2 kilojoules of energy. So we have 8.6 times 10 to the 2 kilojoules of energy released. And this time, what do I want? One mole of CO2. Is that true? It makes 1 mole of CO2? I haven't checked the equation yet.
Yeah.
Yeah? Okay. And what am I going to put on the bottom? Cool. And when I do this, kilojoules will cancel with kilojoules, and I will get what? 3.44 moles CO2. What do I now do with that information? Now I can put that into this equation, right? Does that make sense? And that means here, it's just a matter of plug and chug, as my physics prof used to always say. Which is, you plug all the numbers in and then you just do the algebra. It makes a lot more sense in physics, where you can sometimes have like just monster equations set equal to monster equations, and it's like solve for this variable, and it's just lots of algebra. The algebra here is not bad. We did 1 division and we had it, right? What's my temperature again? Please don't. It makes me uncomfortable. What's my temperature here? Temperature. 290 Kelvin. Good. And down here? Awesome. All right, and I wish I'd made all this stuff a little smaller, but go ahead and do that calculation for me, please. And guys, if you didn't leave yourself enough room, just highlight what you wrote and shrink it down a bit to make some extra space for yourself. Yeah, and move it off to the side. You have to press the button on your pen, otherwise it doesn't work. Just don't forget that, okay? The button. I don't know what to tell you then. Push the button on your pencil, that's it. Okay.
No, you press the sharp button.
All right, I regret this joke already. We should have on the order of what, like 50 something? What do we get?
81.
Really?
Yeah. I got 82.
Oh, that's 290. Yeah, okay, that makes more sense. What'd you get? 81.765?
876.
8765? Okay. And if we go back and look at the numbers we used, I had how many sig figs? 3, 4, 2, and 4. So the answer should go down to 2. Yeah, no, so hear me out. When we add, we go to the nearest number. This is ambiguous. This depends on where you apply your sig fig rules. I would be happy with this if you gave me 1 in your answer. I'd be happy with this if you gave me 2 in your answer. It's a place, by the way, where sig fig rules break down a bit. And that's why, again, if you're an analytical chemist, we have more robust methods in place. So if you called this 80, I'm happy. If you called this 82, I'm also happy. I'm going to call it 82. And 82 what? Liters is right. Okay, listen up, guys. There are some practice questions on here. Do them. I also threw some practice questions that reach back to units 2 and 1 on there. Do those. We don't want to forget that stuff. This isn't like grade 11 chemistry where we constantly use every skill. So I'm going to now start building in practice questions from previous units as well, so we don't forget. All right? Do them. Have a wonderful day. Be kind to one another. Don't forget you have an assignment package that is due Wednesday. Likely not. Were you absent Friday? Then probably not. It'll be somewhere, so it's also online. I did throw a PDF of everybody's online. Maybe I didn't. Maybe I said I was going to do that and then did not. But anyway, if you come find me at lunch, I will get you your printed copy, unless it's right here, which it totally is. So you can come grab it right now. Is anyone else missing the assignment package 3.1? or if you prefer, 3.1. All right. Also a French teacher.
What up?
Howdy. How you doing?
I'm doing all right.